All right, so we're going to continue with the flyweight pattern today, and the idea that we want to implement is a bunch of trees that are randomly showing up on the right hand side of the screen, and they're sort of like moving all along to the left, and it's almost like we're running through a forest at that point. And we'll have them randomly display, but the flyweight pattern is going to allow us to share the shared components or share the common components of each of those trees so we don't have like this huge objects hanging around. And apparently that's what the flyweight is about. It's that's what the name is. We're flying weight off of the object. I don't know about the fly part, but the weight part is definitely that's definitely what it is. So if we want to create a tree, we can do so in source here. Create a tree.rs. Pub struct tree. And what are the common things that a tree needs? Even if I think about like all the things that a tree needs. But the common ones at least to begin with it. We need a location. So a location, which is going to be a vector 2. Use ggz and algebra. Vector 2. Okay, so we need a location. We need, it's going to be moving to the left. So that will also be a, I'll just put everything into here and then we'll remove it as we decide like what exactly we need. Either that, or I could try doing this on the whiteboard if I get that set up. See if it's actually set up for me. I have like a camera that kind of sort of pointing towards it. And I just set it up the other day, so this will be awesome if it works. Let's see if I do studio mode, whiteboard, position. Yeah, that a little bit better. And the windows are open, which is causing a little bit of glare. But if I ignore that, I think that we can use this. So let me go ahead and switch over to this. And we're back here. I also didn't check to see if the audio was working for that, so hopefully it was. Video mode, we're back to this. Wake up. All right, so we know we don't want to store the location is fine because that's going to be different. For every single tree is going to have its own location, and then we're going to have the branch color and trunk color. So branch color, and we know this is going to be a color. So type color, and then a trunk color. I misspelled trunk up there. That's cool. So we have our trunk color. We're going to have a mesh, but I'm not going to store it in the tree. I'm going to store that maybe in a different structure that the tree then gets handed. We're going to have, we need to create the tree. We need to remove the tree. Let's see, then we're going to have a location. We have that already, and velocity is going to be shared as well. So this might be all the things that we need. Oh, a size. We need the size. Oh, right, because we're going to have different size trees can be there too. So we have a trunk width F32. Trunk height F32. And I think that's going to be everything. Let's pull off of this, and then we'll create a new tree. And we're going to want to create the tree off of to the right. Because we happen to know what the size is here, we should just take in the arena like size, and we'll have the tree create itself in the appropriate spot. So if I have the arena width, and I'm going to need the height too. We're going to create a new tree. All right, so public function new here, the arena width, okay. So I guess the first thing, let location equals, well, I guess we can't do location. We need the width and a height to figure out how far to the right to do it. So let's do that. And I guess each tree is random, isn't it? So we want to bring in rand. Do we have rand? We do not. Oh, that's weird. 0.7.3. Don't do it twice. I must have double clicked it by accident. Now that means we can pull in rand. So use rand prelude star. Let mute RNG equals, so what is this? Rand thread RNG. And so our location, the width and height, that's what we're doing. So width equals RNG dot gen range. Let's make it anywhere between 5.0 and maybe like 15.0. So like a really big tree. And then our height. So that, and I guess this is trunk width. Trunk height. Trunk height equals RNG gen range. So I'm thinking this will be anywhere between 10 and maybe like 25. So we can have super tall trees too. All right, so that gives us our width and our height. Now we can give our location. Oh, and we probably, I guess like right before the location, we need to figure out like what are the length of the branches. So that branch size equals, let's do trunk. I think it was based upon the trunk height. Trunk height. And if I want to do that, if I just wanted to make it like the same as the trunk height, and it just goes and it's the same down, same like sort of diagonal across, that might make like really, really long ones. But I can also have the branch sizes be a random number too. Now that we have this, let's do that. And we're gonna do it between the trunk width and the trunk height. How about that? How about that? That might be interesting. We'll find out. Okay, so the location. We want to make sure that we're to the right edge of the screen. So that's going to be a vector2 new. The x is going to be the arena width plus the trunk width. We're already on the left-hand side of the trunk width. So that's going to be fine. But we do need to add the branch size. So branch size, that should be fine for that. Now that's the x. The y is we want to go down to the arena height and then subtract the, I guess the trunk height. And I think that's where we're going to start drawing it, is at the trunk. And then we're going to go into sort of like the negative when we're creating the mesh for the full, what is it called? For the full tree thingy. Now what's interesting here is if I'm doing this like with different sizes, that may be a problem. Because then they need different meshes. I think that we're not gonna be able to do that. I think if we're gonna have like a trunk width and a trunk height, this is probably gonna have to be part of that mesh. And it's only the trunk colors that we're going to be able to truly have be unique. So unfortunately, width and height probably are gonna have to go into this other trunk, like the trunk mesh struct that we're gonna pass in, which we probably need to pass in here and then store a reference to it locally. Yeah, so this entire thing we did with trunk width, trunk height, I don't think we want them to be random like this. If we're gonna want something about like the size, we can have a scale and then scale them at draw time. So we can have a general like a scale like that, but that's different. So unfortunately, I don't think. Well, we can do it our random number generator. So trunk width, we're gonna make this a scale, and let's make this a scale between negative like 1.5. And maybe 1.5. So not a huge variety between them. But the rest of these, yeah, unfortunately, we're not going to be able to do that. Now, location. So we can't really do our location unless we know the size of the tree. So we need that other, we're going to need that shared struct and then pass that in here. So while we're sort of in real building this, let's go ahead and start building that out. So what did he call it in his? Open up. Let's see, that's command pattern. If we go to the next chapter, that's flyweight. He called it tree model, which makes a lot of sense to me. So if we have a new file called tree model.rs, pub struct tree model. All right, so what's in here? The colors are unique, but this is where we need the size. This is where we need the trunk width, F32, trunk height is an F32. We don't need the colors because those are going to be set elsewhere. So I might have these just be white on here, then we apply the color somewhere else. And then we're going to have a velocity. Okay, so a vector 2, so that here we can have a velocity, which is a vector 2 of F32s. And then a mesh. We're going to need the mesh itself. So use ggz, graphics, then the mesh and the mesh builder. Okay, let's implement the tree model. So pub function new. When we're creating a new one, I don't think that we need anything special in here. When we create the mesh, however, we're going to need the context. So we do need a context, which is a mutable reference to a context. See. So we need a context. We're also going to need a game result. Okay, so context there, and we're going to return a game result with, I guess, the tree model in it. All right. So once we have this, let's go and start like creating these things. Trunk width and trunk height, we're just going to set these to be whatever we feel like setting them to be. So let trunk width equals, let's do something like 10. That trunk height equals maybe 25. Then we'll set our velocity. And let's just try -1, 0, just like in the P5 one. We'll just see how that works and feels. And then our mesh. So that mesh equals our mesh builder new. Okay, so the first thing we want to make is the rectangle of the trunk. And that's really interesting because if we have the rectangle of the trunk and we need to color that separately, that's going to be a little bit difficult if we combine them together into the same mesh. So maybe I need to store two meshes, one for the trunk and one for the trees, like the leaves. So we have the maybe trunk mesh and then the leaves mesh. Okay, so for the trunk mesh, mesh builder new, we want to make this a rectangle, so we need a draw mode too. Graphics, draw mode. We're definitely going to fill with this one. Okay, then we're going to have the bounds of a rect, which means we add another rect struct here, so we can create that at this point. So rect new, and then the x coordinates of the y, the x and y. We know we're going to create this at like the 0, 0. So we're going to start with 0.0, 0.0 for the x and the y, and then the width is going to be our trunk width. You need to be proper snake case, and then our height is going to be the trunk height. And then we have our color, and I'm thinking we want to set this to be white. And the reason why I want to set it to be white is white, when you add a color to white, it's just going to be whatever color that is. Come on, mouse, work with me here. My mouse sometimes double clicks on its own, which causes weird things like that to happen every once in a while. All right, so white. That's the trunk then. Actually, no, that's just, well, let's see. We have a rectangle. Yeah, that's just the trunk at that point. We don't really care. We're going to move it around to be where we need it to be. So then I think rectangle, what do you return? You just return the self. So then we're going to build this. This is where we pass it into context. We're going to question mark, semicolon that, and that way we can now put the trunk mesh into the struct as we return it. And let's now do the same thing with the leaves mesh. So mesh builder, new. And here we're going to have triangles. So it looks like we can create multiple of them. And it's going to be a reference to points. Create a new mesh from a raw list of triangles. The length of the list must be a multiple of 3. So it's a bunch of points. I wonder if that means... So we have like a... Oh, it must be a multiple of 3. Okay, so we have like the first point, second point, third point. That's the first triangle. And then a second triangle is just another set of these points. Okay, so it needs to be a reference to an array. Let's just go ahead and create that array here. So I guess this is going to be leaves points. And it's just a straight up array like this. So the first point, or the first triangle. So up on top, this means we do need a point 2. All right, so that's going to be the middle of the trunk. So we know that's 0 plus half the trunk width. So we're going to do 0.2 new. The x is going to be half the trunk width. And then the y is going to be subtracted minus. So we need to know what the sort of like the size of these arms are. Let this is going to be like the leaves size. Length is fine. And let's do something like I don't know, 75. Just some randomly pulled out number. It'll make them really long. Okay, so we have our leaves length, and I guess this might be better as branches. I call it leaves mesh, so leaves is right, just to be consistent. All right, so then here we want to go up all the way. Do I want to go up all the way, or do I want to go up half the size? So we're starting at the top of the trunk. Oh, I want to go up half of the leaves length. So this is going to be 0 minus. So it's really just going to be a negative of leaves length divided by 2.0. So that's the first. That's just the first point. The second point is going to be to the left. So we're going to do at the so we want, I guess, from the middle of the trunk. Let's see. That's down by half of the Y. And I guess we need to find the middle of the trunk. So the middle of the trunk is going to be the trunk width plus, I guess it's going to be, I mean, we know this is the middle of the trunk on the X, but then we want to subtract this by the leaves length divided by 2.0. So both those should happen first. That's going to be the X, and then the Y is going to be the same thing. We just want the leaves length divided by 2.0 for the Y. Okay, next for the other side here. 0.2 new, it's going to be the exact opposite. So from the middle of the trunk, so divided by 2.0, we want to now add the leaves length divided by 2.0. That's the X, and then it's going to be the same Y. That's one triangle. So if I start here, and we'll just sort of see how it looks, and then we can add more of these in as we go. So our triangles is going to be a reference to the leaves points. And then the color for this, I'm thinking we also want this to be white. Now, what do you return? Oh, so triangles returns a game result. So I have to question mark that, and then I can build this, and the context, question mark that, and now I have an actual mesh. And I think that's the last of it. So now I can come down here, and we're going to return an OK tree model, the trunk width, trunk height, the velocity, the trunk mesh, and the leaves mesh. Do I not have you auto saving when I? No, I do have format on save. Okay. I was expecting that to sort of change some of the things around, but I guess RLS decided not to, or is RLS not installed? It should be installed because I shouldn't be getting these autocomplete without RLS, I don't think. Oh, you know what it is? I think this is something that VS Code doesn't necessarily run these unless they're connected to like the main application. So I need to now in the main library, we're gonna mod the tree model, and let's go ahead and also just mod the tree at the same time. And now we can use use tree model, and use tree. And I think that's going to cause it to have like to figure out if there's all those problems or not. Now we know that we need to pass in a tree model to tree when we create it new. So here in tree, we know we need to use super tree model. We're just going to need to store the. Do we need to store this in here directly for the actual tree? I think we do. So I think we want to store the tree model directly inside of a tree, but this is going to be a reference to it. And so references inside of structs are interesting because we're going to run into lifetime issues. But let's see if this will work for it, because the tree model is being passed into it. Library is going to hold on to it for us. And since the library lives longer, that means the tree model should live long enough, and hopefully everybody should be super happy with this. So we're going to say we want a tree model, and we want this to be a reference to a tree model. Now this is going to yell at us because it's going to say, hey, look, you can't do this, expected a named lifetime parameter. So I can say that this is essentially tree model like that. Use of undeclared lifetime tree model. Well, now I need to declare that up here. I think that's here. Or it's over here on this side. Expected one of. Okay, so that's not how I do it. Is it just space? Now it's been long enough since I've done this that I can't remember off the top of my head. I don't think it's the and. I will have to go and look this up. Let's go look up Rust by example struct lifetimes. Oh, here's this. So it's there's no at. There's no and. That's what it was. We still need this thing. Like that. So this declares and names the lifetime. We're using it here, and we're attaching it to this reference tree model. Now notice also I'm using like a full name for this. That's because I was looking over here because I can use the camera over on this side. It's up there now. So in Rust, you can have full names for your lifetimes or generics or any other properties. I'm now able to say like, hey, this is the tree model lifetime. And I guess like it's gonna make it just a little bit easier to understand. I could just name it A, which is a lot of people, and all the documentation seems to do that. but I don't need to do that. I could also just name this like the tree lifetime. Okay, so we have implement. Now tree itself needs to use this same lifetime. So we're going to say, hey, look, you're going to make sure that the tree model lives this long. Use undeclared lifetime. Wait, is it off of back here? Or is it now I need to, is it off of the impl or is it off of the tree? It might be off the impl. Explicit, deleted, lifetime. Oh, okay. So it wants it up here. No, whatever that was, don't do that. So it wants you up here. And use of undeclared lifetime name tree model. Oh, do I have to just use it now? So where's the tree model? I haven't like actually created it, used it. Or do I have to do that? All right, we need to go look it up again because I forgot how to use it in these structs. This one seems to have it, I think. I mean, so you can see it in the function. Wait, do I not need it off of the impl? Oh no, I do. Okay, so it's on both of them. Oh, okay, so I need it on both. That's what it is. So I need you here, copy you, and pull it off of here too. So we define it here, and we use it here. All right, so pub function new. Okay, so we're creating our tree. We now need to take in a reference to the tree model here. And this is going to be a just a reference to a tree model. And I believe this is where we need to say, do we need to say its lifetime? I don't think so. And this is yelling at us that we're not actually returning a tree at this point in time. All right, so back to this. We have a randomized scale for when we're creating this tree. We have, okay, so we need to figure out what our location is. So unfortunately, like we don't have the branch sizes anymore, but we can get that from the tree model. So in the tree model, if we have a lens here for the leaves mesh, so maybe pub function get leaves size. This just uses self, and I'm going to return an F32. So we can return let self dot. Oh, we're going to need to store this. We're not storing that. So leaves size, leaves length. F32. So leaves length goes down here too. Let's go ahead and name that the same thing. Self dot leaves length. I can now copy you, go back over to tree, and we can say, okay, branch size. We want to make sure that we're to the right of whatever it could possibly be. So that's going to be our tree model dot get leaves length. Chantilly, hello. Good morning. Happy Monday. Okay, so we're now like over to the right of the screen, and then we want to make sure that we're down far enough. So that's going to be the arena height minus, we need to figure out what the trunk height is. So that's going to be the same thing. We're going to add on here. Pub function get trunk height self F32. We're going to return self dot. Did I store this? I did. Trunk height. So then over here, tree model. So arena height minus, this is going to be the tree model again. Dot get trunk height. So that should be the location of where we want to put it. We need the branch color again, and this is going to be using that random number generator. So let branch color. We're going to create a color new, and then it's going to be RG and B. So we know that we don't want any red. The green is going to be our gen range. And what is our branch color going to be here? It's going to be anywhere between, I guess, maybe like 50 and 255. And then our blue. Our blue is going to be 0 to 0. And then our alpha, I think we want to set this to 0 to 1.0 here. Oh, and these need to be floating point numbers. Then our trunk color, which is, I think, going to be very similar, except we need to do something like that's more brown. So you are going to be trunk color new. What is a mix of brown? It's sort of like everything together, right? Let's go find like a brown color. Maybe like dark brown. Maybe something like one of these, like this one here. Can I get an eyedropper? I can't. Maybe this one. So if I do that, it copies. I hope that's RGB. It may not be. Let's see if it is. No, unfortunately. I mean, that still might be RGB, but it's in hex, unfortunately. So I need to know what the coordinates of these are, but not as, yeah, and just like normal RGB. I like there's a bunch of examples of things that have brown in them. Ooh, here it is. Okay, so dark brown, RGB, like 35, 25, 20. I believe that there's a way to tell. So instead of color new, let's do color. Yeah, from RGB, and then I can do a U8, which I think is through 255. So here it is 36, 25, 20. 36, 25, 20. The alpha is 1, but that's fine. Right now, we can always change the alpha at like the render time. So that's our branch color and our trunk color. We want our scale. So we already have a scale. And then the tree model, which we're also storing, which we have now. So let's now return a new tree. And we're going to put in location, branch color, trunk color, scale, and then we're going to have our tree model, and it's going to be a reference to tree model. Now, does this... Okay, no further lifetime errors. You're upset because that's not something you want. All right, there we go. I was expecting it to like reformat that as I was going. So I'm glad we're at least getting there. So now we want to create a bunch of trees. Maybe like right now, let's just create a single tree. We'll store that and we'll get that drawing to the screen. But we know we were going to want to create a vec of trees. So this is going to be our trees. It's going to be a vec of type tree. When we create a new game, we now need to make sure that we add in these trees. Ooh, missing. Okay, so I need a lifetime parameter here too, because this has an instance of a, well, it has its own lifetime parameter in there. So to remind myself of which lifetime this is, we're going to use the same name, which is tree model lifetime. So help consider using the lifetime tree model. Oh, interesting. Okay, so tree model like that. That's how I do this lifetime here. Is I'm just saying, okay, this is the lifetime you need. Now, when we import my game, we remember we have to declare the lifetime here. So tree model lifetime here, and we will use it here too. Now, when we go ahead and use this, we need to create a tree and add it to the game. So I guess we're gonna have our trees be just a good old vec to begin with. And then we'll just add in a single tree in right now. So that's tree, new. We need the arena width. I think we already have that. Arena width, arena height, and then a reference to the tree model, which means we need to create that first. So we should store the tree model here so that make sure it never goes out of scope. And we need to make sure that Rust knows that. So we're going to hold the tree model. Now, if necessary, I can pass in a tree model each time to tree whenever it needs to use it, and that way it won't feel that it has to store it. Storing it is just a little bit more convenient for us. So you're going to be a full tree model. We're not gonna have a reference for you. So tree model equals tree model new, and the context and question mark that because it returns a game result. That gives us our tree model. We can now pass in a reference to this tree model. It'll yell at us because this is going to go out of scope, but not a problem because we're going to store tree model right here. So we have tree model and then trees. Now we have some errors. Implicit deleted lifetime not allowed here. Oh, so now we're gonna need to add these lifetimes to all of these different areas, all these impls. So I think impl tree model for my game tree model. Let's see, so we're not using you. Let's get rid of you. Let's get rid of some of these warnings too. Okay, so mismatch types, expected floating point number, velocity. I just forgot. What is this? Tree model. Or, yeah, that's right. And then found expected. We need a semicolon there. Cannot return value referencing local value tree model. Returns a value referencing data owned by the current function. So this is basically saying, hey, look, you have trees, which is taking in a reference, but you're returning it. So therefore it's going away, and it's going to be dead. So I'd need, I guess, tree model is borrowed here. It returns a value referencing data owned by the current function. Yeah, so even though I know that it's okay, Rust does not. And so this is where it's saying maybe you shouldn't program in this way. So if I didn't want to program this way, which will make it a lot cleaner too, because I wouldn't need all these lifetimes everywhere. Save you. If I come here and I say, okay, I'm not going to store the tree model, which means I don't need these lifetimes. I'm going to take it in as a reference here, but I'm not going to store it. I'm just going to use it temporarily here to figure out exactly where we're going to go. Like to get our location and all that stuff. And then this still works here. We come back to the main library. We now need to get rid of this tree model. Lifetime. Just you go away. And we're going to store the tree model, and we're going to store a vec of the trees, and that's going to be fine. And this is going to be fine, and this is going to be fine. And notice, let's see, problems, no errors, just warnings, just a bunch of warnings. Okay, we'll get to some of those later. So now we have our trees. Let's go ahead and draw our first one to the screen. So here in graphic, okay, so in graphics draw, right, so in draw, we have our, if we're playing, we draw all these things. We want to draw the trees first. Because that, yeah, we just want to draw the trees first. I could create another function for it to sort of like draw them out. That might be a good idea. We'll just sort of add them in up here. Let's see, fold, update. And so here's all these other functions like draw help screen. Add you in here. So function, draw trees. We're going to have self. We're going to bring in context. We even have the trees, so I don't need to like pull that in. We're going to return a game result. Hopefully has nothing in it. Then we're going to loop through all the trees. So for tree in, we want to reference. So a reference to self.trees. Okay, so now we have a tree. We want to just call its draw method, which means we need to add a draw method into here. So pub function draw self. I guess we do need a context, don't we? So we need context. Graphics. Oh, that's off of just GG Easy. Context out, and we're gonna need context and game result. I'm sad they didn't auto bring that up. I figured it would like sort them based upon, you know, alphabet or something. That'd be nice. So mute context here. We're going to return a game result. And a game result that has not whatever you are. Nothing in it. Okay, so we just want to run the draw command. So we need graphics too. But not only that, we're going to need a reference to the tree model too. So the tree model, which is a reference to tree model. And now I believe we can finally do graphics draw, pass it in the context, pass it in a reference to the drawable. So that's a reference to the tree model. And in reality, we really just want a public function get. We want the trunk first and then the leaves. So get trunk mesh, a reference to self, and then we're going to respond. So if possible, I kind of want to return a reference to a mesh. And in here, we're going to turn a reference to self dot, what is it? Trunk mesh. And we want to do the exact same thing. So pub function get leaves mesh self return a reference to a mesh. Return self dot leaves mesh. Okay, get trunk mesh, get leaves mesh. We can now use those here. So the first thing we want to draw the trunk first. This is going to be our tree model tree. So this is going to be a reference to tree model dot get trunk mesh. Let's just draw the trunk first and see how this goes. Then our draw params. Graphics, draw param. Draw param. Let's just do default. If I do this, I think it's just gonna draw it in the top left. I mean, we could find out. And then we're gonna. Actually, I don't think I need to even semicolon that. Let's see what this is. Draw returns. What are you on me about? The traits, mesh. Okay, the trait bound a reference to graphics mesh. Graphics drawable is not satisfied. Drawable is not implemented for a reference to this mesh. The following implementations were found. Interesting. Okay, so if I had just created the mesh as it were, a mesh is drawable though, isn't it? Oh, I don't think I want to use a reference there. I think I just want to get that, and it's already a reference. Okay, so now this works. If I come back to the library, we're going to call the draw method. So it's tree.draw, and then we need to pass it in the context, and then a reference to self.tree model. And we can semicolon this to make sure it goes up to the game result. Now for you, mismatch types, expect enum, standard result, found nothing. Right, because if we reach the end, everything was fine, and we'll just return okay. And now we need to run draw trees. That's down here. If we're in a plain state, let's go ahead and call self.drawTrees, pass it in context, and semicolon. No errors. Let's see if we get a tree in that upper left-hand corner. There it is. That's our tree trunk right there. Now we need to sort of change its color. That size is really, really, really small. We probably want it to be significantly bigger, but we can fix that. So all the trunks are of the same size. So in this trunk model, so we can just come here and set, well, your trunk width, we need like, I don't know, 25 at least. Trunk height, you need to be way bigger. Like, let's make you like 150. Leaves length, we need you to be like at least 250. And that should be fine. But now let's move it over maybe further to the right and down a bit. So in our tree, when we set our location, let's not set it fully to the right of the screen. Let's set this maybe minus that, so that way it's just a little bit to the left of the right hand of the screen. But we also want you on the ground. So if I do that, hit save. So you're up here still. You're significantly bigger. That's better for a tree. But we need you to be down here. So where was that? That's so our location. Oh, because we're not sending it to a better destination. So here in our drop params default, we now need a .dest, and here's where like a point that we want to set to. So we can say a point to, which we need to pull that in. Okay, so for the X and the Y, that's going to be just our location. So self.location.x, self.location.y. See if this works. Yeah, there it is. Okay, so we can see that it's the branches are going to come out probably around half this point, but maybe all the way over. It'll be interesting. We can play around with that. So now I want to, well, we created a tree. Let's make the tree, well, let's color it. Let's color the trunk here. So we have our destination. Part of draw. Okay, so then here we're also going to do dot color. And we're going to do self.trunk color. I think, do you need to be reference? Or do you take a copy of it? I think it takes a copy of a color. So it's going to clone that. So we say view, and now it should be whatever sort of dark brown this is. There we go. That's maybe a little bit too dark brown. It's very difficult for me to see. If we go back to here, we find here this cocoa brown might be good. This is 210, 105, 30. So now notice that I'm having this just be a solid trunk color. Let's just make this part of the flyweight then. The tree model holds the trunk color. Everything's the same. I don't need to overwrite it. And then it's going to be smaller, well, smaller everything. So in tree model, when we create the trunk, so the trunk mesh here, instead of white, we need to give it a color. So graphics, color. Color from RGB, and then what was this again? It was 210, 105, 30. Now if I save this and we just rerun it, it should, we have an error. Trunk color, a field by this name exists in self. Where is that? Oh, right, because we're no longer, we no longer need that. We're no longer storing it there. No longer store it there. Okay, no more errors. Let's run this, and we should get the better trunk color just displaying for us. I should probably run cargo run. I don't know why I run code dot. There we go. Okay, much easier to see. I mean, maybe it's not a very beautiful trunk, but this is definitely something we can update, change out, and it's all in one place in that trunk model. Okay, so next up, we want to now create the branches around. We already have the model for that. So now it's just going to be telling when the tree draws, we need to also draw this too. So we're also going to graphics draw, pass it the context. The drawable is now going to be the tree model dot get the leaves mesh, and then the params. So if I don't change anything about, we'll see that also in the upper left. Draw param, default. We know we're going to want it to set it to a destination. So let's figure out where we need to put this. The tree these tree points are based upon where the top, it's new. So its center point is based upon like 0 minus, I think I can just tell it where the center, I might have to give it to the center of the location, but I might just be able to give it the like the location that I have. So let's try that. So our destination is a point to new. I want to put this, the x as our location. So self.location.x, and then the y is the same one. Self.location.y. And then we'll just return. So this one, we're going to question mark, semicolon this one, and then straight up return this last draw. And that will be our game result. if we run this, that looks exactly right. It's centered on our tree. As far as I can tell, it's huge. Maybe, well, I don't know. It might be fine if we run this again. That could be good. We might want it just a little bit higher, maybe to just, we could have a taller tree branch, tree trunk. And I think that will just make it a little bit better. So tree trunk height, if we just set this to like 250, I think it will look a little bit better just on its own. Yeah, and so now if I have like 2 or 3 of these sort of tops going down, that will sort of like look exactly like what we had for P5JS. So let's now draw out. Now what's interesting is I don't need to create that those leaves mesh again. I could just draw it again, but give it a slightly lower location. So let's semicolon that. Let's draw it one more time here. Graphics, draw, pass it the context, do the tree model, get the leaves. I'm gonna draw param, default, do a destination, point 2, new. We know we want it to be the self-location.x, but then a y is going to be self.location.y plus something like 25 down. And you need to be question mark also. Now if I do that, we should have 2 sort of like stacked on top of each other, just like that. Now we can now get into a really, really interesting idea here, which is because the tree is concerned with how many sections of branches that it has, we could do our loop through here and then just choose, well, how many do you want? Now we already have our RNG at this point in time. Let's store our RNG out in the main component, and then we can reuse this a couple different times. So in our main library, we're going to want to use RNG prelude. Oh, it's rand. Prelude like that. Let's store RNG in here as a thread range. Now when we create this, that's just up here. Let mute. I think I need to create it as mutable up here. RNG equals rand thread range. So that creates that. When we create our tree, instead of this RNG right there, we're going to bring it in. So RNG, which I want to be a mutable reference to a thread. Is it thread range? I think it is. So I don't need you anymore, but everything else should just work. And this also means that down here, I'll be able to use to get this RNG passed in. So RNG, which is a mutable reference to thread range. So now we draw the trunk once. We're going to do 4. I do care about this count. So we're going to do tree count in. we want this to be a floating point number. So let's do 0.0 through dot dot. Actually, I don't. It'll make this a little bit simpler. So 0 through, let's say up to 7. Not inclusive. So that'll be up to 6. Then I want to draw our tree here, but our self.location.y, we're gonna say that plus, and it's gonna be 25.0 times our tree count dot into. We just need to convert that into a floating point number. Cannot infer type for type F32. Wait, how do I do plus with that? Cannot infer type for type F32. Well, I know you're an F32. Do I need to say 25 F32? Oh no, I think this one can't. So you know, instead of into, can I do F32 like that? Say what I want you to go into? No. We'll just do an as F32. All right, and that should give us now a whole bunch of trees. And this, we don't need you. Now, because I'm I'm doing all those in there, I need to now return an OK like this. All right, so in our main library, we're storing, we're grabbing RNG here. So when we're creating our new tree, we need to also give it a reference, a mutable reference to the RNG. And then we need to store RNG here. And then finally, when we draw, so I can just fold everything. We open up my game. Actually, no, we just need to open up the implementation of my game. Go to the bottom here for draw trees. And so for in tree.draw, we also need to pass in a mutable reference to self.rng. Oh, so I just need to do that. Oh, you need to be mutable self, because unfortunately RNG needs to be mutable. So then this is there. No errors. If we run this, we should now get a whole, a very interesting looking tree. Maybe too many. That just goes all the way down to the floor. So maybe not quite that tall, or we increase the height again of the tree model. If I increase the trunk height to I don't know, 5, really, really tall. And probably doesn't need to be like that tall. It could be significantly less tall. So 550, 350 is probably fine for this. There, that's fine. And now I want to color the leaves. And that's going to be pretty simple, because here in tree, we're going to do the exact same thing that we did sort of do with the trunk before we decided to make it in the global there. For the tree count, we're going to draw. Here's the draw params. Your dot color self dot branch color. And now it should be whatever random branch color that we've decided to make it. There we go. I think we can also set that to be sort of like have a little bit of an alpha, but let's see if it's viewable as it is right now. Now, okay, next thing, we want to make the trees move to the left constantly. Well, we already have a velocity, and that's in the tree model. Now we're going to want to have an update method on tree here. So we have draw. So we're going to have update. We know we're going to want to mute self. And we're going to want to take in the tree model, which we know is going to be a reference to tree model. And I don't think we need to return anything. All we're going to do is update the location. So we're going to say self dot location plus equals tree model, and then we're going to want to get that. Let's create a lens to get the velocity. So hub function get velocity. We're going to take it self, and I want to return a reference to a vector 2. F32. So we're going to do a return a reference to self dot velocity. So that should make that happy. Then in tree here, tree model dot get velocity. Semicolon that. All right, so then an update. Let's do this again. So in the event handler here, we're going to update in our match while we're playing. We have this entire, like, if we're like get the, like, figure out what command we're running and then hit that. I just want to update our trees. So at the bottom here, we want to self. Oh, we need to do this for all the trees. So we need to loop over all the trees, and then run those. This is probably something where we can do off of the impl my game. We can have a function update trees. This is probably going to be mutable self because we need, stuff inside of the self is going to be mutating. And then do I need context? What does the update function take? It takes the tree model, so it doesn't. I don't think so. And I don't think I necessarily need to return anything here too. We're just going to loop through all the trees. So for tree in reference to self.trees. And now we're going to call that update. Call the, yeah. Is it the update function? It is. So tree.update. And it needs a reference to this tree model. So we're going to do reference to self.tree model. And then we can semicolon this. Oh, right. We need to borrow this as mutable. And now we can call update trees right here in this function to sort of like slowly refactoring this to be a little bit cleaner as we touch it. I'm not going to do this like big giant cleanup all at once, just as it makes sense. I'm going to call self.update trees. And that's it. This should now update our trees every single frame and make that tree move to the left. Let's find out if it works. There it goes, and the tree is moving to the left. It's moving at a different pace than the other obstacles. And that's just because, well, I mean, that's what we did with the other game. And I think it works. It should show us that it's in the background. We can have it even move slower for us, which might really help make it look like it's in the background. So that's in the tree model. Let's change that. Let's make it half the speed. So negative 0.5. All right, so the tree is moving. Now we want to create a tree and add it to that. Add it to our vector of trees randomly. So I think we chose in the other game like a 20% chance. We can maybe do a little bit less of a chance here in this case. Maybe like 5% chance, 1% chance. I don't know that it creates a tree. We know that when it creates a tree, it creates in a right position to the right of the screen. So let's do that next. Which means in our main library, let's create another function here. Up here, create tree. So function create tree itself. Okay, so we're probably gonna need we might need context, we might not. Let's find out what we need, and we'll add that into the signature of this function as we need it. Chantilly, it'll be funny if you add a random branch or a squirrel on the tree as another form of obstacle. Ooh, interesting. That could be something where like it's potentially like hanging down off of the trunk, and then you have to duck underneath it. Ooh, that could be really fun too. Let's add that into the README. Let's see, nice things to have. Suggestions. Yeah, get poked in the eye by the branch. So let's see, add an obstacle hanging off the tree like a squirrel. All right. Now, so in create tree, we want just a randomized chance to create a tree. So let's first start with that. We'll do let. I guess it'll be if. Let's then generate the number. So self.rng dot genrange we can do this between 0 and 100. So if that is less than, let's just say 5. If that number that we create is less than 5, then great, we're going to create a tree at this point in time. So self.trees.push. Now let's push a new tree into it. So this is going to be a not tree model, tree new. Okay, so we need the arena width, the arena height. The tree model is pretty simple. We already have that. And RNG, we already have that. So let's grab the arena width and arena height. So let's arena width, arena height equals graphics drawable size, which means we need the context here, which means we need to pull that in here too. Now, okay, so arena width. So we have arena width, we have the arena height. We need a reference to self.treeModel. And then we have our RNG, which is a mutable reference to self.rng. All right, so we're going to push a new tree in, and then I think Method, okay, and yeah, then it's just saying, hey, method is never used. So let's go ahead and use the method down here. Create the tree. Pass it in context. Save that. And let's see how many trees end up getting created. That is still a lot of trees, 5%. Now I think a big part of this is because we have what? Oh, we're down to 18 frames per second. So just adding this in is just a huge strain on the system. Let's rethink how to do that so that we don't have to like 80 frames per second every single frame, run that calculation. What if I do something like every x, not every x frames, but every x seconds, create a tree, and then when we create the tree, we could randomly choose the next group of seconds to create the next tree in. Then we'll wait for that time to happen. Then we could just calculate how many more seconds it is that we need to wait for. That might work for us. Now, if we store in my game here, if we store game's timing starts at 0 and it's tracked in milliseconds, I believe. So if we want to store when to create the tree, so create the first tree at. So create tree at. We just set this at 0. We're going to create a tree right away, like immediately. This is I think we can do a F64. It's going to be whatever our like duration time at is. So we may have to change this. So when we create a new one, create tree at. We're going to set this to 0, so we create a tree right away. Create tree at, so store that in here. Mismatch types found. Oh, I don't think it's an F64. I think it's going to be a U64. Okay. So that makes you pass. We've now we need to decide if we need to create our tree. So in our create tree, we need to get the time, like get the current time. So that current time equals, I think this is off of timer. There's average delta, check update time. Time since start. This is what I want. So returns the time since the game was initialized. All right, so we get the time since start, pass it into context. Now we can do an if here. So if the current time, if that is greater than or equal to self.create tree at, we want to create our tree. However, if it's less than, I can do an early return and not have to do the rest of this. Let's just do that. If this is less than self.create tree at, let's just return early. And we're not going to return anything at all. Although in this case, I could return a game result. only so that I could return okay and actually have something that I return at. All right, so what are you? You are a type duration. So I need dot. We can do as sex. Now, what do you return as? A U64. Okay, and so you are a U64. That's perfect then. And maybe I want to do as sex right here. So as sex. I don't need to run you again. You're fine. So if it hasn't reached the time yet, return early. Otherwise, we're going to do the rest of this. We're going to get the arena width. We're going to get the arena height. We're going to push a tree in. Then we need to... we don't need to do this self-degen range thing anymore. We just need to straight up push a tree in. But then we want to now calculate the time to create the next tree. So self dot create tree at. Let's set this equal to the current time plus self dot rng rng.gen range. And let's make this between maybe like 1 second and 30 seconds. And then finally, we'll just return okay at the very end. So this should be a little bit easier on our system. We're still calling create tree every single frame, but we're just doing a quick time check and then returning early most of the time. Let's see how this affects our frames. I mean, it's still down there. But you notice we created 2 trees right away. Oh, I think that's because I start with a tree, and so it created the second tree immediately. And now it's creating trees sort of randomly after that. So I think this works. I'm down to 47 frames per second, which, I mean, part of that is because I'm in like a virtual window, and part of it is because I've given myself like less resources than like the main computer while I'm also streaming at the same time. And of course now have like lots more things that are rendering and creating to the screen, screen here. If I build this in release mode, it'll be significantly faster and nicer because GG Easy also is significantly slower whenever it's rendering anything in dev mode. So I did that. Let's now move our trees over to the right. So it's in the appropriate spot. And we also want to make it so we don't start with a tree right away. So when we create a trees here, let's just have this be an empty vector. And when we create our new tree, our location here, that's going to be up here. Our location is plus. Now it should just nicely create trees for us off the edge of the screen. It sort of looks like we're running up towards them, not just like teleporting in. Exactly like that. Perfect. Now when they get off to the left-hand side of the screen, we want to get rid of them and delete them. And that's going to be interesting. So there's a couple ways we can go about and do this. We can try to mutate the vector of trees and delete them from there. But we don't necessarily know which ones to delete. So we can use like a filter and sort of like create it back in there. We can have regardless, we should have a function in here to help us determine if we're off the edge of the screen. So pub function is off screen. So we just need self. We're going to also need the arena width. And we're going to need the tree model too. The reason why we're going to need the tree model is that entire size, because otherwise we're not going to know how wide we are. So tree model, which is a reference to tree model. We're going to return a Boolean. Okay, so we know we're off, so we're going to just straight up return. Actually, we don't need arena width, do we? Because we know that 0 is the left of the arena. So if we're at 0, essentially it's going to be 0 minus. So if our location, so self dot location dot x, if that plus the width of the trunk and then the width of the leaves, that will give us like the most safety here. So this will be the tree model dot get. We have the height, but we don't have the width, do we? So on tree model, we have get trunk height, pub function get trunk width, F32 there, and we're going to do self dot trunk width. That should be good there. Here in tree, so get trunk width plus the tree model dot get the leaves length. So if that is less than 0, then it's true. So is off screen. This will be true if we're that. Let's make this an F32 with 0.0. So now in our main library, we can now run this function to see, is this specific tree off of the screen? So there's a memory intensive way for us to deal with this. And like maybe it's the more naive way to do it, which is duplicate the tree vector and then overwrite the main tree vector every frame. So if we close down up to trees and get trees, and now we're going to want to destroy trees off screen. We're going to mutate self. I don't know if we need context or anything else right now. We might. And I don't know if we need to return anything. We're just going to mutate the trees vector. So one way, we can try running like we can consume the trees vector and like create a new one. So if I do that new, we just call it trees because it's different than self.trees. So that trees equals, then we're going to do self.trees dot, let's convert it to a iter, let's see, returns an iter that is modifying each value. I don't actually need to modify the value. Into iterator, create a consuming iterator. That's fine. So I'll create a consuming iterator. Now I can filter off of this. We're going to hand it a, we're going to get a tree in here. And for my tree, I want to return true or false depending upon whether or not I want to keep this this tree. So this is going to be tree dot. Do you know what you are? You're a type tree. Tree dot is off screen, and I need to pass it in a reference to self dot tree model. And at the very end of this, I have an iterator still because I believe that filter type mismatch and closure arguments. Expect signature for a reference. Oh, it's a reference to a tree. That's what I'm getting, I think. A reference to a tree. I think I don't even need to tell it what it is. I think it should figure it out on its own. It just wasn't, so I needed the type hinting. Now at the end of this, what is this filter returning? I think it returns a filter. Creates an iterator which calls this closure in each element. If the closure returns true, the element is returned. Yeah, it returns an iterator. Then I want to collect this into another vector. So dot collect. But I don't think it'll know, yeah, type annotations needed because collect doesn't know what it is. So trees, you are a vec of a tree. Cannot move out of self.trees, which is behind a mutable reference. Can I? Move occurs because self.trees has type of centered vec tree, which does not implement the copy trait. Well, I kind of want to move it out of here. Now, if I just do iter, now collect, a value, a type, a vec tree cannot be built from an iterator over elements of a reference to tree. So then I want to take ownership of these trees. Now, I suppose that I could just copy this. Now, if I copy it, trees doesn't implement copy. So I need to come back to here and derive. Now, this is something that like I'm still learning with Rust, and I would love to know like a better way that I could do this. Instead of copying and cloning it, what can I do to like now I guess specs and an ECS system would actually help out here a lot because that's exactly what it's made for. So I don't have to do this type of thing and copy all over the place. So an ECS system would be right. Now I don't want to do that for this game here because I want to keep it. I don't want this to be about ECS. I want it to be about this. Of course, unless the book has us do ECS. Well, we'll see. So copy. We're going to copy trees. I guess it's clone. We're going to clone trees, turn it into an iterator, and then collect it. And so this is going to be an into iterator. So that way we take ownership of this new clone. We collect it into this new trees. And then we're going to do self.trees equals trees. We're just going to completely overwrite it. So as the tree goes off the screen, it's going to be dead. Like it gets removed completely. So we're not going to try to update it anymore. We're not going to try to draw it to the screen anymore. It's just gone. And that vector will grow and then shrink as time goes on. So if we save this, and we run you, Now our game is about what we had it before. We're losing frames as each tree gets created, but at least once the trees start going off the left of the screen, it should be fine again. I guess I could create a counter for how many trees we have like in memory at any one time. We're down below 60 frames now. I might want to try rebuilding this in release mode just to see where that gets us. The trees are very slow. I do like them. I don't like the color of the tree is pretty sort of like standard here. There's not really too many variety. Like there's not very much variety. Also, I feel like every single tree has the same number of leaves, so I think we may have screwed up somehow with that. So as this one goes off the screen, it should disappear, like get destroyed, and then get back. It's slow because it's having to render all of these shapes, and even though it's a reference to a mesh, it's still like GGEZ is really slow at rendering. Whenever I guess it's because it's all these different triangles too. That's another problem here. But at least we shouldn't go any like slower than about this. One thing I'm noticing is that my for loop here, I think is wrong. Like for tree count, oh, it's always 0 to 7. I need this. We're getting RNG. I really want you to be RNG.gen range between 1 and 7. That's what I want to do. Yeah, it actually says in the documentation for GGEZ that GGEZ is really slow when rendering lots of stuff to the screen in dev mode. In release mode, it's significantly faster. And we can actually try that. Let's try run release. Because at this point in time, I think we're done with the pattern. Because once we start deleting those, then it's gone. So while this is sort of running here, let's do a quick recap of what we did. We're implementing the flyweight pattern, which means we, specifically flyweight pattern with a bunch of trees. So we have a single tree model that has all the unique things about a tree. You can see that here. It'll surprise us when it starts playing. The width, the height, and let's see, the location of where it is, the color of the branches, and we're not even using scale for this. I think we can even remove that potentially. That reduces the size of each tree down quite a bit. Now the tree also has all these methods that pretend that we have the full tree, including the mesh there. But we take in a reference to a tree model. The tree model is a structure that holds all of the non-unique things, all the shared things about each tree. So that would be the width and a height, the velocity of the tree as it moves along, the mesh of the leaves, and the mesh of the trunk. Our main owner, so the main library, is in charge of holding all the trees, but also the one singular tree model, and then passes a reference to that tree model around, so that way it can be used by all of the different trees. So you have a whole bunch of trees, still only one tree model. This is significantly faster. Let's do that again. Yeah, we're at like 130 frames per second now. Now we're getting that flashing is actually caused by little problems with. Oh, you know what it is? I need to store. It's the random number generator. That's the leaves of like every frame. It's like, oh, well, I get to choose how many leaves I have this frame. We should probably choose in the tree how many leaves it has, like when we create it. So here, instead of this scale, let's just do leaf, like leaf count. So this is gonna be leaf count is a, we can have this be whatever we want. It could just be a U8. We know it's gonna be very small. So save you there. Then this will be leaf count. We have our leaf count. We have our RNG. So instead of gen range that, it'll be gen range between 1 and 7. Then we'll hold our leaf count down here. Then we'll use it when we draw. Instead of this RNG gen range here, we'll just do self.leaf count. And that should make it not do whatever that is again. Now the problem with doing programming in a release mode all the time, even though you get faster, specifically in GGEZ, is I don't get as good error messages coming out. So this one has 2 leaves, that's fine. But the game is a lot more playable, specifically in this mode. Maybe I do need to change. Oh no, there, here, now we're getting a forest. And we can see the frames per second dropping down. I dropped into 80 when it created these. And specifically while I have a huge number of the leaves. But at least everything is a little bit different now. The trees are all like, it is also fascinating when they come in clumps like that. But that's that. So what else do we do? So we have a tree. We have the tree model that holds all the shared stuff, and then we just have methods on the tree itself, where our main library here can call them. The only reason it knows that the tree may not be everything that it is that because the tree needs the tree model to do anything. Now, I could store the tree model in the tree when I create it, but Rust doesn't believe us when we say, hey, the tree model is going to live a long time. Yeah, it definitely is going to live a long time. So therefore, you can go ahead and don't die. So with that, oh, destroy. You know what? We never called destroy trees off screen. We need to do that to actually make them go away. Self.destroy trees off screen. Just like that. And that is it. That is the flyweight pattern in Rust. Oh man, I suck at my own game. Does anybody have any questions? I'll try playing it and looking over to see if there are any. I want to get through at least to see like a tree move to the, oh no, I died. I want to see like a tree go to the other side of the screen. What happened to the trees? You know, I'm a little bit worried now that I'm killing all the trees before they're reaching the other side of the screen. That's that might be something that's happening because I'm now destroying all the trees. You have a result that needs to be used. Okay, so destroy trees off screen. We're gonna filter off, you know what? I keep on doing this all the time. We don't want is off screen, we want is on screen. So I can just use this as positive and keep it. Otherwise, I need to have this just be the opposite, return not tree is off screen. That's what I want to do. Now our trees should all come. They'll move. They all have consistent branch sizes. They're not like spamming like crazy. And then as soon as they get off to the left, they should die. I wonder if that. Do we make it wait too long? Oh, I made it wait like because it has a chance to wait up to like 25 seconds sometimes. And so that then disappears. And is gone forever. We can add in a tree, like a tree count, just like to show that they are really disappearing. But that's not really part of this specific example. So I am going to save this all up. We'll put it up onto the onto GitHub. So implemented Flyweight Pattern into Rust Infinite. Push that on up. Each tree reduces the frames per second like 20 to 30 frames per second. Yeah, it can. The best thing for me to do probably would be to limit my frames per second to 60, which would make the computer a lot happier. And I think if I do bang repo, yep, that is a link to the code, where the code is.